In a previous part of lecture, I mentioned that when light propagates in a material, some of light is absorbed, and now we will consider this effect of absorption of light. If we have some piece of substance with thickness L and a ray of light with intensity 0 passes through this material, sum of intensity, so energy of light, is re-emitted in secondary wavelengths, but some of the energy is distributed in the material due to interaction of oscillating electrons with surrounding atoms, and this part of energy is spent on increasing of internal energy of this piece of material, that is on heating of this material. Then the intensity of the ray in the exit of this piece is lower than intensity of initial ray, and it follows from experiment that this intensity I is I0 and E minus kappa L. L is this distance, and kappa is coefficient of absorption. This relation is named by Bouguer, so this is Bouguer's law. Now let's again look at previous lecture. At the previous lecture we obtained this dependence of this relation in which we mentioned that at resonance frequencies we have regions when maximum of absorption occur. And indeed, if we look at behavior of this coefficient of absorption, we will see that in many cases we can observe some separate lines. Here is lambda, here is kappa on lambda, and at some lambdas we have strong absorption and practically no absorption in between these lines. This is a specific figure for absorption in media, which is, for example, a gas at a low pressure when particles of material do not interact with each other. And in this case we have this picture, but if the pressure is increased, then some interaction result in spreading of these lines, and at high pressure we will have some envelope of all these lines, so it will be uniform, or at least not separate lines, but spreaded broad region in which absorption occur. By the way, such materials like metals, which contain a lot of free electrons, they completely absorb all the light which falls on the surface, so they are not transparent. But on the other hand, if we have a vapor of metal atoms and this vapor has low pressure, we will see again these separate lines which correspond to dependence on coefficient of absorption on lambda. Now, in addition to absorption, we will consider another effect which is specific when light passes through material, and this effect is scattering of light. When we consider how light is propagated inside material, we mention that electrons here start to oscillate, and due to these oscillations they emit secondary wavelets, and in principle it could be expected that these secondary waves which are emitted are distributed in all directions. But if we take into account that these secondary wavelets are coherent, it in principle can be proved that as a result of this interference of these coherent waves, all the waves which do not propagate in the same direction as initial beam are damped, and so the direction of the beam, the only intensity which remains is in the direction of the initial beam I0. This is in the case when the medium here is homogeneous. So it is absolutely homogeneous without any particles inside, and then this is in that case that we have only one beam which follows this direction. But in the case that there are some particles, small particles inside, for example, in this case this medium is inhomogeneous, and in case it is inhomogeneous, for example, this is something like fog in which we have droplets which are suspended in air, or for example it is smoke with small particles are suspended in air, or maybe some emulsion in which we have some water in which some small drops of fat are distributed. In all these cases we have scattering on these particles due to diffraction, and due to diffraction on this inhomogeneous these particles which create the volume inhomogeneous, we obtain diffraction, and this diffraction results in scattering of light in different directions, distinct of homogeneous case. And if this light is scattered, so this results in decreasing of intensity of light which covers this distance. And at the exit here, in addition to absorption, we have additional decreasing of intensity, and this decreasing is also exponential, and in this case we have additional coefficient here, and this coefficient is called coefficient of extinction. So kappa prime is coefficient of extinction. the case when particles at which this scattering occurs have very small size, and the typical size we will describe some dimension of a particle we will describe by some effective radius of this particle. And if effective radius of this, not necessarily that it is spherical, but it's effective radius, and in case r is small and much smaller than lambda, it follows from experiment that in this case light is scattered light is polarized. It is easy to understand why. If we have light which propagate in this direction, then electrons, we have here in this light, we have E vector which oscillates in different directions. And when we consider this light entering inside material, we have here some electron in material, and this electron and other electrons will also oscillate in this plane, which is perpendicular to the direction of distribution of propagation of light. And secondary wavelets are also, E in these wavelets is also oscillate in this plane. It is easy to understand because why it is produced this secondary E in electric field, because charge is shifted in this direction. So when it is here, for example, minus is here, then minus is here, so it results in oscillating of E in this direction. Then if it oscillates in this direction, for example, if we consider light which is scattered and right angle in this direction, we have no such components of E vector, only this. And then in observing the light which is scattered at right angle, we will have completely polarized light. It is evident that in the case we consider this light from here, we have both this direction oscillation and this direction oscillation, so it is not polarized. Then it is easy to extrapolate for some intermediate case. So in this case, light will be partly polarized, because partly this projection of this oscillation will made in this direction and partly in this direction. So if light is observed at the right angle, so it is scattered light is completely polarized, and at intermediate it is partly polarized, this scattered light. In the case when r is very small as compared with wavelengths, this light which is scattered depends on the intensity, on the frequency of the oscillation. So it's on the wavelength of light which is scattered. The intensity of scattered light is proportional to the fourth degree of frequency, or it is proportional to 1 on lambda in the fourth degree. It is easy to understand from consideration of energy which is emitted by electrons, and this energy is proportional to the fourth degree of frequency. We cannot prove it, but this in principle it can be derived. Now we can just believe that it is correct. And this dependence of scattered light, I mean not light which goes through, but of scattered light, And this intensity, this dependence of intensity on the wavelength is called Rayleigh law. By the way, I forgot to say that this media which contain many different particles, they called turbid media. By the way, this Rayleigh law explains us why the sky is blue. Look, if we are in the globe, and we are here, and sun is here, and we look at the sky, then the light which reaches us is not direct but scattered. When we look at the sky, we see scattered light. And according to this Rayleigh law, we see that in case that lambda is shorter, scattering is greater and the dependence is very strong. So a blue part of spectrum is scattered from light, from air, much greater than red one. You can ask me why we have scattering from the air, because it is easy to suppose that at high altitude air is not turbid media. And then what are these particles at which the scattering occur? The answer is that in this case the scattering occur not on the particles but on the different domains of gas, small domains of gas, in which due to chaotical movement of molecules of air, somewhere the density is greater, somewhere the intensity is lower, and this difference in density produce quasi-particles at which this scattering occur. By the way, sometimes you can see that when, especially after rain, when ground is warm, you can see that air is like some medium which is thin. The same the same law can explain us why sun is seen as red when it is low at the horizon in the early morning or in the evening, because if sun is here and now we can look on sun, and in this case we look at sun, and in this case light goes through a thick layer of atmosphere, and on all this way we see not scattered light but direct. In the same time, blue part of the spectrum is scattered, again as in that case, and so the light which reaches us is enriched with a red part of the spectrum. So this is the last part of today's lecture, and actually this is the end of optics at all, and now we are ready to pass a midterm test.